And we want to be in time. Welcome to our fourth day, and today, after having sessions and days on quantum computing, data, the compute continuum, today the real thing, modeling the digital world, is coming to you. And we have one session this morning with two speakers, Wolfgang Reisig and Peter Tettke. And Wolfgang Reisig will tell us, I cite, one and for all, how to build these systems and to model these systems. Some short words on Wolfgang. I will introduce Peter later on. He's a professor emeritus at Humboldt University. I've read with salary. I have to ask him how to do that. It's at Wikipedia. And since 2015, he studied in Bonn, did his PhD in Aachen, and his habilitation when he worked at the GMD in St. Augustine, also in Bonn. He was then some years at the TU Munich as a professor, and afterwards for more than 20 years a professor on software technology and theory of programming at Humboldt University. So, it's your turn.
Okay, thank you. Ladies and gentlemen, the title is a little bit provoking, I know that.
No, we hope, it's a promise.
Yeah, we start with a prelude, and the first point of this prelude is a remark on Frank, of course. This is tradition in the way that I have to say something about Frank, but it is a little bit positive, so don't. So Frank is smart, and Frank loves heavy math. On Monday, those of you who have been here on Monday have seen how much he loves heavy math. I love tiny and elegant math. That is something different from Frank. Okay? So what does it mean? It means to start with a very small amount of assumptions, and then you get amazingly interesting consequences from those tiny set of assumptions. That is what I would like to use today for showing you why this title of the talk is justified. But I second start now. The first start was about Frank. The second start now is about software engineering. I very quickly go through this history, and I show you why this history is not so good as it should be. So what is the idea of the problem of software engineering? Somebody has an idea in his mind what he would like to have built in software, and then he must have bridged this gap, and usually this gap is not bridged very well. And that is the state of the art. And there was a very famous, or later on very famous, conference in software in Garmisch-Partenkirchen, where they said we must make now this very elegant bridge from intuitive ideas to software. And the result was we need better programming languages. And I think this was already the sin and the mistake and the stupidity to start to say we need programming languages. We need something else, and I will tell you what we really need. So then they said not just Fortran, but they started, there's some monster languages, the elderly of you may know, Algo 61, PL1, Ada, or tiny ones like Pascal and Simula. And then it continued programming paradigms, logical, functional, object orientation, engineering. And engineering is the problem. We must make engineering. Software engineering. Again, the mistake to focus on software, requirements engineering, software life cycles, design methods, waterfall, all these models. And then came a word, the first reasonable word was model-based. Aha. So before you start to build a house, you make a model. You go to an architect. You don't go to the one who puts the bricks together, say, make me a wall and make me an open space that will be the window, but you go to an architect and he makes a plan. So the fundamental idea is, before you start coding, you make a plan. But you want to have coding. That was revolutionary, because until nowadays, people start coding before they start thinking. Okay, So construct a model before you start coding. That is a fundamental idea. So there are some typical modeling techniques. You can read them here. It's an alphabetic order, nothing reasonable. And if you miss your own modeling language, no problem, put it in here. There are so many modeling languages around, and I will say later on, no, here. I want to go back, yeah. I will later on tell you why all these languages are not what we really need. So the starting point was to say, do you have an idea? No. Somebody has an idea and wants to make a software. And that is already the stupidity. When you have an idea, you want to make a system and not just a software. The system includes people, and somebody has to sign a contract, for instance, that is part of the system. Or the system includes some technical aspects. So what the client wants is not a software. The client wants a running system. And what you have to model is not the software, but the system. And that is a fundamental difference. There is this notion of software modeling. Such a stupidity. When you have a software, you don't need a model for the software. The difference between the model of the software and the software itself is not really great. You don't need a model for the software, but for the system. Okay, and now I want to continue. Yeah, this was the modeling techniques. They don't really help. So what we need some models, that is very true. We have these techniques here, but these techniques are not what we really need. Okay? So what do we really need? What is a good modeling technique? Well, no, the order is wrong. So what is wrong with these modeling techniques? Well, they either argue from the perspective of computing, then they are quite formal, or they are blah, 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 some informal things. What we really need and what we can do is formal models for the system part, for all the three parts here, not only for the software, but for everything in the system that you are interested in. Okay, so a good model separates components. That is a very important aspect. Talks about real-world items and not only about data, but also about what is going on in the real world. Formulates behavior, refines and abstracts models not just as a tree-like refinement, but some refinements have a joint refinement down, etc. A lot of things like that. And you as a modeler, that is a fundamental difference to the programmer. The programmer is given the level of abstraction. The program tells you in what detail of the level of abstraction you have to argue. If you don't like this as a modeler, you want to choose the model of abstraction yourself, the degree of abstraction. The modeler chooses the degree of abstraction. When you have such a good model, you can formulate, improve system properties, you can assess complexity of behavior, you can explain everything to the stakeholders. You cannot, of course, you cannot go with a program to the stakeholders, what is done nowadays. You can estimate costs, you can formulate agreements and orders. So if there are a fight between the software house and the client, then it is the model where you should look and say, look, this was what we have agreed upon. Okay, you have to can specify functionalities and warranties, etc. That is, that is what you really want, and the question is, how can we achieve this? And the first point is, well, what is the difference or the path between the real world, which is here, and the model which is up there? There are three aspects important. There is architecture, there is components, composition, etc. There is static aspects like data and items that are in this system that you want to say, and its dynamic behavior. These are the 3 points that you must integrate into a good modeling technique. Okay, and if you want to have details on this, I recommend this book that is now in print and will be available in some weeks. And there you can read all the details. Because today I do not want to speak about the whole world. I want to speak about one aspect, which is a fundamentally important aspect, and to show what you have, what you can do there, and why that solution that we propose is not just the 1001st solution, but the one and only one you need. So today, me as well as Peter, we will speak only about architecture, so only about this column here. Okay, and the rest you can read in the book, or come next week, next year here, or have been last year here. Then there we have spoken about the other two columns. Today only about the architecture. So that was the title, once and for all, how to compose modules. And there is a calculus for that. Okay, and as you remember from the three columns, only the left one. That is what we speak about today. So what justifies this talk's title? Well, there are already available a lot of case studies in various domains. There is a quite innovative application of that is large process models, and that is the next talk given by Peter. He speaks only about this one aspect. You will see how general this composition calculus is. You will, and I give you already a glimpse on this. A model is just a graph. There is nothing more general than a graph. An interface is a set of vertices of that graph, and they are labeled and ordered, and composition needs nothing more. So I think already now you see there is nothing more general than that. Composition is technically simple. I think that is important. It is total, which means you can in principle compose any two components. It's not always very sensible, but technically you can compose them. And now comes the point of my talk today, mathematically deep and practically useful properties. And this tiny kind of mathematics, that is I want to show you. So now my talk starts, and I understand also now my 50 minutes start. Is that true? I just said, now my talk starts, and I hope that now you start running the time, which unfortunately we do not. Okay, so I will go through this quickly. So now I speak about, now it becomes a bit more technical, models and their composition. You all know what a graph is. This is a graph with nodes and edges, and it is a directed graph. In this talk it's irrelevant if it's directed or not directed. The examples are directed, but everything works also for undirected graphs. Okay, this is an interface. An interface is just a set of nodes, nothing else. And each node has a label. And this triple case, every label is the same, namely label alpha. Okay, here's another graph with another interface, and at least one of the nodes, this one has a label beta. The others have all label alpha. Okay, now composition. What means composition? You compose A with D because they have the same label, and this is the composed label. You compose B with E. They have also the same label as here. You cannot compose C with anything because there is no other node left here with the label alpha, so C remains. And
Wolfgang, this composition is not unique because I could merge A and E.
Okay. You see, a good talk is cheating a little bit. Yeah, and I hope I can cheat you, but you cannot cheat Frank. Okay. Okay. So I have to go a little bit more to the details of this. The node A is not just a node with the label alpha, but the first one in this row here. So A is the first in this row, D is the first in this row, okay? And therefore you compose A with D, the first with the first, and not A with E.
That means there's a structure on top of the graph that orders the nodes.
No, not all the graph. Only what you really need only the order is inside single interfaces,
okay.
And they are only those who have the same label. Only those are ordered. And therefore, well, yes, but you're right. So what remains is C and F, and they have no partner, so to speak. And what can we do with C and F? They go to the interface of the compose system. So this is now the interface of the compose system. I think everybody who starts a little bit playing around with component models and composition starts this way. And this is very nice, but it has a big mistake, a big disadvantage, namely it is not what we call associative. So when you first compose, when you have three of them, you first compose A with B and then C, then it's in general different from composing first B with C and then A with O. I don't show you the example because Udo will not give me the time to do that, but believe me, this composition, as simple and nice as it is, has this deficit, and of course you want associativity, otherwise you don't. So what you started with is very elegant, but not good. But what we do now, we change a little bit the idea, and then we got it associative. Okay? Another try. So we say this now is no longer just a graph, it's a module. And the module has a left part, a left margin and a right margin. So on the left margin is the left interface of the module, and on the right margin is the right interface of the module. And likewise here you have a module, so this is the left interface, this is the right interface. And now you compose them exactly in the way that we did already, namely the right interface of the left module is composed with the left interface of the right module. And what you gain is this, with the fundamental difference now that G remains here, K remains here, but now C and F, which we had as an interface before, now they move a little bit. C goes to the right and F goes to the left, because C was already on the right part, F was on the left part, and that is now the new definition. And what we will see later, this is associative. I expected you to act differently. I expected you to jump on the table and say clap and say wonderful, that this is associative, unbelievable. And it is unbelievable. It took me almost half a year to prove that. It's not at all trivial, but it is true. Believe me, it was published in Acta Informatica. Who knows this journal is, what is in this journal is true, because the referees are so strict in this journal, so it is true. Okay, so, and they retain their label. That is all. And now you say, well, why just two interfaces? It is really useful, and there are so many examples. When you get used to it, you go through the world and you always find modules with a left and a right interface. So for instance, we have here a composed system, raw material, supplier, manufacturer, etc. They all have in a very natural way a left and a right interface. And at your end, you just compose them without brackets, because it's associative. Or another example, you have an input side and the output side, customer, supplier, requester, provider, consumer, producer, buy side, sell side, predecessor, successor, etc. The world is full of modules with the left and the right interface. And that's all what you need. Okay. And now we come to the mathematical part. And before you go out, I promise you, it is so elegant, simple math. It's not like Monday. Now it's really something that you can love. First point, of course, is associativity. That is the most important thing in this context. So that means if you have three modules, then the brackets don't matter. The brackets don't matter. And you can just write n modules, compose them, that's it. Associativity, well, I give you, how much time do I still have?
30 minutes.
30 minutes, okay. So I just want to show you that this associativity is really not trivial. So we have here a, we have a module L, empty left interface, and the right interface, one element. We have a module, why is not written M, which we have, it is M, one left, one right, and if you compose them, of course, you compose A with B, R composed with M, and C remains in the right interface. Okay? And then you have, now I confused everything. This should now be L. No, it's N, that is right. And now you compose R composed with M with N, and there you see C goes with D because both have the label beta, and C goes with D is here, A with B is already there, and this E has no partner, it goes to that. Okay, now let's look at the other point. First we compose M with N, so this is M. This is completely different, so we have the C with label beta that goes with D, okay, and what remains is this B here and the E here. So now you see L composed with M and M composed with M are completely different modules. And if we now compose M composed with N with L before that, what happens here? So B goes with A, okay, and E remains, and what we get is this one, opposite, and surprise, surprise, it is the same, despite the fact that in between the things are really absolutely different. So this is an example that shows you that this is not trivial. Okay. So the next property is called cancelativity. That is only a word in algebra. Nobody knows this. The question is, when you compose two modules, is it like scrambled eggs, where you cannot identify the components at all? Or is it like words over an alphabet, where you say when you have two long words and you compose them, and when you know where you have composed them, then you can recompute it. Yeah. So how is this composition defined? And the answer is very clear. It is like the words over an alphabet. And in mathematical terms, this elegant, simple mathematical terms means if you have three modules, and if you know R composed with M equals R composed with N, then you can, so to speak, divide by L both sides, and that says L composed with M is only equal to R composed with N if M is equal to N. Okay, so that means you can divide by L. Yeah, you retain the information of the components. And instead of, yeah?
I can read this as an exist. If there exists an L such that this holds, then M and N are equal. Is it not? I mean, the way you write it is like that.
No, it is.
Yeah, let L.
And if this is the case, if this equality holds for any L, then this holds. But that is, I have written this. If then.
You've written it.
Okay. And the other way around, you have seen this, one must also say the other way around. If M composed with L equals N composed with L, then M equals N. The L may be left or on the right hand side. You agree? So many of properties that are really useful in applications have this purely algebraic spirit. And that's what I wanted to say. So the composition behaves more or less like words over an alphabet. This more or less I will talk about, because the next property is commutativity. So is it true that M composed with N is always the same as N composed with M? And the answer is clearly no. In general, it is not the case. But sometimes it is the case. So then the algebraic question is, when is it the case? When does this hold? As I said, not always, but sometimes. And the theorem says they are equivalent, N composed with N and N composed with N are equivalent. I don't tell you what. Equivalence means almost the same, up to the order of the relevant elements in the interfaces. It's the same. So if, and the composition is commutative if no label occurs in the interfaces of M as well as in the interface of N. So if the labels are completely detached, then you can compose them in either order. And
I don't get it. No label occurs in the interface as well. So they have no label.
You have your labels, I have my label.
And not the same label.
Not the same label.
Okay, yeah.
Yeah.
The sentence is incomplete.
So if our labels are completely detached, that means they don't compose in any reasonable way. They're just side by side. Okay? And then you can make them this side by side or this side by side. If and only if. Okay? Again, an algebraic property that is for applications very important. And this can be used to parameterize modules. Once you have more or less the same module, but you want to run them with different parameters. Then every parameter is a label, and the labels are all different, and that means you can order them as you wish, or run them unordered. Okay. And here's again an example that shows you also now the notion of equivalence. So we have the property, a very simple module M. It has a left interface labeled alpha, right interface labeled beta. Then we have a module N. Its left interface is labeled gamma, and its right interface also labeled gamma. So you see, alpha and beta is for this module, gamma is for that module. They have nothing, no label in common. So what happens when you compose them? Then, for instance, M composed with N looks like this. Here is the A, and here comes the D. And on the right-hand side here is the F, and there comes the C. So in technical terms, this is the formal composition of N with N. And this is the formal composition of N with M. This seems to look a little bit different. Namely, the gamma, the D, which is here on the lower side, is now on the top, and the A is now on the bottom. And also here, the C, which is here on the first one, is now here at the bottom, the second one here and here. But this order is completely irrelevant.
No, you said the order is relevant when I asked you that is not unique what you teach to me.
Order is relevant if the labels are the same.
Awesome.
If the labels are the same.
Yeah,
but here the labels are not the same.
Yeah.
So those two are equivalent. And I showed you.
Why did you change gamma and beta like on the left-hand side? So why did you cross that out?
And that is due to the technical definition. Technical definition says, for instance, here you say, first take all the elements of the left below the M, and then below that do the other ones. And here you did it the other way around. But I told you this example because there are two other equivalent representations of those modules, namely this one. So this crossing here is not at all necessary. You can write A, B, C. So A, B, C. You can swap this again, and D, E, F here. And now you can also swap the two lines in the same way. You have D, E, F on top and A, B, C on bottom. Okay? So you have a certain kind of freedom in representing that. And I think we all agree that these representations are even more beautiful than those two. Okay? So the notion of beauty is very important. Good mathematics, Frank, I tell you, good mathematics is beautiful. It's not technical, but it's beauty. And here you see the beauty of mathematics.
Okay. What is the interpretation? So if the two modules are completely independent,
yeah, so that means that means that's what I've shown you. That means that example comes now again. Completely independent means their labels they have not the same label. Yeah, question.
So far we've looked at the interfaces, but do you ever have to look inside the box? Is this a black box or a white box?
The inner, you speak about the, but I ignored the inner for a while. I have a good point. My first set of a property only talks about the interfaces. So inside maybe whatever you wish. You can write a text inside, or a picture, or a smell, yeah, or a program. Don't write a program. A model, a patronage, beautiful. Yeah. So you can write inside whatever you wish. I only speak about properties, so far I speak about properties of the interface. Later on I speak a little bit about also the inner. Okay.
So
Hmm?
at the moment it's black box.
Yeah, okay, let's call it black box. No, let him ask. It's better to ask.
The equivalence that you just showed us by example,
Yeah.
you don't have that as laws, because it's not talking on the interface level. Right? You have laws here like conductivity and so forth and so forth, but what you have to do inside there, you don't have laws.
It is, what means a law? It's a property
That you can swap, for instance.
that you can swap. You can swap differently labeled elements you can swap, and it's the same. Well, I have, now, if to prove that or to justify that, you have to speak a little bit about the fact that the whole system is a graph. And as a graph, it is exactly the same graph, only a little bit differently presented. Okay. So now another example for commutativity. So you have this composition. You composed R with M. Again, M is missing, and you have this composition. And now I'm confused. I've forgotten why I made this example. Why on earth have I made this example? Can you help?
It's not commutative because you have better on both sides, right?
It is, yeah, that's what I wanted to say. Yeah, thank you.
Same label.
Yeah. So those two are not commutative because they have beta on the same side. They share beta. Those two are not commutative because they share an alpha. But if you compose P with N here, or N with P here, then they are commutative with this N. Because now P composed with N has a beta. What did I can tell you abstractly what I wanted to make with this example. It is if you have a big box which is commutative with a small box, then they may be commutative. But if you open the big box into small parts, then you cannot exchange all the small inner parts. You cannot swap all the small details, but when you make a big box, then you can swap the two. I'm sorry, I've lost the dramatic idea of this example. Yeah, another algebraic property is called equidivisibility. I must confess, I didn't know this word either until recently. It is a fantastic property. I love it. So assume Q equals R and N and also equals K and L. So you have M and N composed, K and L composed, and they are the same in Q. And they are not commuted. So M and L, you cannot swap M and L, you cannot swap K and L. So here's a graphical layout. Q has an M and an N, and if you compose them, they are in order, so to speak. And now we also say, aha, we can also say there is a K, and the K is a little bit bigger than M. Then, of course, the L must be smaller than K. You see, because M and N composed with N and K composed with L is the same. So this is the situation. And now comes the algebra and says, then there exists a unique module P that has a certain property, that is this one here, namely that the Q you can write as M composed with P composed with L. So the smaller of the components composed with this new one composed with the smaller of the other composition again are the module Q. And that means if you have two different decompositions of a big module, so you decompose the module Q in two different ways, maybe once in M and N and Frank does it in KL, then we say, of course, this is the same, and we even have a unique component in between. So you can say it as follows, as I said here. If you refine Q once with M and L and the other way with K and L, then there exists a P such that M composed with P composed with L is again the Q.
Why is non-commutativity
Important, let us make an example and you see it. You need the order, yeah.
I can now do the same for K and L. So there should be a P prime so that K, P prime, N holds. And that doesn't really fit the picture because I don't take the larger ones.
Among all these candidates for P, there is the biggest one. And for you, I tell you another story. It is just a push out of category theory. Some people are happy with this information. I was happy 30 years with this kind of information. Meanwhile, I hate it. It is so senseless to make this category theory. Like you, I know you like it, so for you it is a push out. Okay. So far I have spoken about single modules. Now I speak about distinguished interfaces, and there is so you will say, what a stupid module, it has no nodes and it has no edges. And later on you will see this is a very useful module. Because for this module holds, if you compose it with somebody, then it has no effect. Aha, some people think already, that's algebraically interesting because it's a neutral element. Okay? And if you say this mod is the set of all modules over a fixed alphabet of labels, then you can say it is a monoid. And as a theoretical computer scientist, you love it. It's a monoid. That is something you can carry home. And you know this already, because what you learn first year course is informatics is about so-called free monoid over an alphabet. Nobody knows what a free, almost nobody knows what a free alphabet, a free monoid is. And I will not tell you what this free means. I want to tell you this one, mine is not free. Free means the only equations that hold come from the associativity. And here sometimes, as you see, sometimes it's commutative, so sometimes hold more equations that are not deduced from associativity. Okay. So, and now comes a lot of beautiful properties. For instance, almost trivial, if you take a subset of the labels, then you get a submonoid of the bigger monoid. And also submonoid is a nice algebraic structure. So now comes something, it's called module is cyclic if the left interface and the right interface are equivalent. That can happen. You start with the interface with blah, 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 and then you come back home, so to speak. Okay, and now we ask, what can we do with this? Well, here is an example. Yeah, this has and now I have a little bit of graphical structure inside, but that's only decoration. We could also prove it out. So we have the left interface, two elements with the label alpha, one element with the label beta, and here also two elements with the label alpha, one with the beta. So this is a cyclic thing. And also N is cyclic. It has left an alpha and a gamma, and also the right an alpha and a gamma. And now guess what the theorem will say? If you compose them, you get a big system, and surprise, surprise, it has on the left two alphas, a beta and a gamma, and here it also has two alphas, you see it here, and a beta and a gamma. Okay? So composition of cyclic modules is again cyclic. I didn't believe this for a while, so I didn't even try to prove that. And then I made a lot of examples, and it always came out. And then there is a beautiful meta-theorem of mathematics. You know the beautiful meta-theorem of mathematics? It says, if there is a counterexample, then there is also a small counterexample. And that holds for all trivial mathematics. And we are all, Frank, I'm not so sure, but I am a trivial mathematician. So this kind of mathematics is mathematically so simple that this meta theory always holds. So I started to try to find a counterexample, and if you don't find one with less than 10 nodes, then you are sure there exists none. Of course, there are famous theorems about number theory, where the smallest example is billions of nodes. But this is real mathematics. And let's be honest, what we are doing is formal blah, 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 but not deep mathematics. So this holds, and is not so difficult to prove as associative was, but it's also not completely trivial. So, when you say cyclic of lambda nodes instead of all cyclic modules, then this is also a monoid. Because the neutral monoid is, yeah.
Cyclic means that n composed with m is identity element.
It's again m. No, m composed with m is two m's in the row.
Ah, so you don't.
I know.
Because you make a.
Yeah, I understand this movement. No. And later on, when I still have time, we come also to this. This is also an interesting point. But here you see, yeah, okay. And now you can do even the following. You say, I have a fixed interface. One and for all, I have one interface called X. And now I'm interested in all modules with this interface, with the same interface. Of course, the left and the right interface of the module should be X. I only know this one, was ist das denn jetzt? Lieber Peter, Danke. Okay, and then I started thinking, give me a real-world example of something where you have one fixed interface and a lot of modules that have all the same interface, left and right. If you compose them, you of course remain in this. And it took me very long to find a real-life example, and then I found one, and that's this. So, the interface is of course the plugs, which is called the plugs. And the plugs of such trains should be left and right the same. Not only this, every wagon should have the same interface. Okay? So there are real world problem examples like this. Okay, here I have an example for this. Of course, if you compose them, then in a way, the left of the left interface and the right interface of the left and the left interface of the right, they match perfectly because they are equivalent. Okay, and what comes out of this? Yeah. So this is again a submonoid. So if you are in this world, and you don't have to fear that you jump out of this world and suddenly you are in the neighbor's garden. No, the garden is fixed. Okay. I'll give you another example. Some distinguished interiors. Now I go a little bit to the interior. And the first modules that I show you is the alphabet module. So you have, say, the classical alphabet that you know from literature, so to speak, and that is sigma is the symbols alpha, the 24 symbols, okay? And now I want to say, aha, in informatics we make these formal languages, so we compose words together. How does this is this reflected here? And it's very easy. So we have a module for the symbol A, and it has inside the module the symbol A, and there is a special symbol, composition symbol, exclamation mark, to the left and to the right. And this is the module for the symbol A. And this is the module for the symbol B, okay, etc. This is the module for the symbol Z. So now we see, aha, classical informatics is nothing but a very special case, an almost trivial case, of this general theory of components. Because now you can compose those, and it's always composable, and you can write big books, so we wrote our books always on this basis. Yes, in classical informatics is the trivial part of composition calculus. And this is a free monoid, and as I said, free means in this context there are not commutativity, and of course not, because the exclamation mark is used by everybody. So every module shares the exclamation mark of every other. Okay. Submodules. How much time do I have? I can also fix quickly, but here we have again a graph. So there's nothing behind, just a graph. And this is a submodule in this graph, because I make now a module, it has a left interface, it has a right interface. And then you can ask, what about the complement of that? It is also a module, so the rest, so to speak. And now this is an example. If there would be an arc here, this would no longer be a submodule. So submodule means whenever the module is somehow connected to the rest of the world, then it goes to an interface, either to the left or to the right. But you cannot jump out of the module not using an interface. So that is a submodule. And with the right arc, it's no longer a submodule. So this, now you cannot see the details, this is the complement of the module before that. That is also a module. Beautiful. Complement is also a module. They share the interfaces. So it's not just the graph theoretical complement, they both share the same interfaces. And and then we have initial and final submodules. So for instance here, then you have, now it ruins my jokes. So you have a graph, not a module, sorry, here you have a module with the left and the right interface, and now you have what we call a cut. In graph theoretical terms, a cut means if you take out all the elements of the cut, you get two detached subgraphs. So with this cut we use to say, aha, we have the initial part that shares with the big module, it shares the left interface, and its right interface is the cut. And you have the final module that has as the left interface the same cut, and as the right interface, the interface of the big system.
But
if you compose,
okay, good. Are they uniquely determined? No.
Are they what?
Is the init and final M, are they unique?
Yes, but if the cut is unique, you give the cut, then they are unique.
That's okay.
If you take another cut, then you get two others. Yeah. And but as I written here, if you compose them, you get back M again. So if you have a big system and you say, I'm interested here to cut out the system, no problem, what remains are two modules. So you can make one module with a cut into two modules. And you're always sure it is a module. You stay in the world of modules. That is the important thing.
But you have to invent the labels, right?
Yes.
You don't know the labels on the card.
Now you have to put on labels. You must make an interface out of the cut. Okay. Now, one aspect that is still important. You could say that in my world, in the composition is so complicated. I love complicated composition, stupid enough. But when I compose, I also want to change euros into dollars and centimeters into yards. And you want to put a lot of things into the composition operator. And in informatics, we have this a lot of culture, you try to do this. Squeeze a lot of things into the composition, which is really stupid, as so many things in informatics are really stupid. And and I have such a simple composition calculus. How can this fix? How can this be put together? And the idea is, just show it to you immediately understand that this is much better. And for instance, here you say, I have this module and that module, and I want to somehow interconnect them as you see here. I want to do this, that is your right, you can want this. And I say, okay, if you want this, no problem. You make a module, you make an adapter in between. The adapter tells you all the difficulties, what you wish. And the adapter has a very simple interface, harmonizes with M on the left side, and on its right side it's harmonized with N. So the composition itself is again very simple in the composition calculus, and all these things that you want to put into the data and items and whatever, you put it inside the adapter. And the intuition of an adapter is absolutely something that has a left and a right interface. So adapter is a fundamental concept of, say, best
Still seem to
practice.
miss something, because if that's the same label, order is important. Don't I have to connect the first alpha of adapter with the first alpha of n? Yeah, this one.
Yes, you have to connect them. Yeah,
But then I get.
this is what the example says. Here you say, I don't want to connect this node with anything. Now I have to connect it with the first label of the adapter. That is true. So what was my trick, so to speak, here? You connect them, but inside the adapter it does not have any relationship. There is no arc starting from this node somewhere else. So to speak, a blind spot. You put it together, but has no consequence.
Alpha and N should go to the other.
Yes.
No, because they fit perfectly. This node and this node.
But you don't need that alpha in the adapter, the first one.
Yes.
You actually don't need it.
If you don't put this here,
This one.
if you put it away, then this node would be composed with this node.
Why?
Because now this would be the first node of the adapter.
Okay.
But the last beta in the left module and the last alpha on the right module, you didn't connect with anything, so they stay open.
Yeah, they stay open. Yeah, if you want it.
Because like the adapter there.
Yeah. Okay. So you see, I'm almost finished. So we can speak about a lot of other topics, and I don't speak about them here. You can buy the book and read them. There are classes of modules, finitely generated, domain-specific classes, patch-minute modules. So in a way, now you have the basis to start. So what you got so far is not the result of anything, but this is the starting point of anything you need in informatics, where you compose two things, do it on this basis. Okay, put everything you do on this basis. And that brings me to the very end. Composition calculus, I'm not sure you are convinced, is no longer just another composition operator, but a fundamental basis, as I said, for any composition principle. There are more algebraic properties worth considering, in particular concerning hierarchies and submodules, best practice concepts as adapters, and domain-specific subcalculi, of course, should be under consideration. It's never too late to start using the composition calculus, and from tomorrow on, please do it. That's all. Thank you.
Thank you. We had another question in between, but I think we go until 11 and then postpone the break for 5 minutes. That's okay? Yeah?
So Wolfgang, at some point you showed that you can do regular expressions, kind of. I mean, you can do the elements. But where's the Kimi star?
The what?
The Kimi star. I mean, so you showed that you can do sequences basically.
That was also his question. Give him another 5 minutes and I started. You can just, I said, if the left interface and the right interface are almost the same, you can also glue them together. That's why I have a new operator. And we even write it with C for completion. And there you have the key. So you need another operator for the key stuff. But we know this and we did it.
You probably know about social factorization. You see the potential of the calculus to improve this very, let's say, pragmatic techniques in software composition?
I have two answers to that. First one, of course I know this, and of course you can do it. Second answer is, I don't really know this kind of stuff, and I only hope you can.
It's a must deal with, misconstructed software.
Yeah. So now, I understand now you have much time left, so do it. It is not my, I'm not, I don't know this.
Okay.
First, I see the modules just for the software. But do you also have the other aspects in mind? So the machine, the people?
That was our main concern. These labels are of course not only symbols. This label, and I have shown you the wagon of the train. So we always had in mind real world modules and not this only stuff of informatics.
Because I see the interfaces like input and output of information, and the inner nodes as some computations, but they have more in mind.
You can do this, but you see, Peter is a business informatician. And for us now, the modules are much more than just information processing elements.
Sharon?
You have on slide number 10 the abstraction, you have the world, then the three pillars, and then the model.
Yeah.
Say architecture, statics, and dynamics.
Yeah.
And I was wondering, does architecture encompass statics and dynamics too? So in other words, isn't the pharmacy of architecture including statics and dynamics? If they are not treated, they are not the same level.
There are two things. Firstly, of course, you must integrate the three aspects, and that's what we have done. I give you one example. Dynamics, if something happens, then it happens inside a module. Classical theory, for instance, automata theory always pretends if something happens, the whole world changes. The whole world is in a global state, and now you make a small step, and the whole world is another step. Absolute nonsense. So you must say, if you have a small world and something happens in the small world, and that is the kind of theory you should start with. So it is not just three pillars that are detached, but they are integrated strongly. That must be the case. And the second was the last remark of yours, I forgot.
No, I still think that statics and dynamics are properties of the architecture.
Yeah. So in software architecture, you really have a dynamic
Yeah,
aspect
software architecture.
itself.
I'm not interested in software architecture. That is
I thought you
old
want to
school.
build real systems.
So far, but it's old school. Forget it.
Oh, I think before this escalates now, as we all have to rethink, we learned yes, we have to rethink our thinking about computer science after 40 years or plus or whatever. So I think the coffee is really needed, and we reconvene at 11:15. Okay, thank you again.